Hey, Rob. Sorry, you haven't been waiting long, have you? Hello?
Good morning.
Hey, how's it going? Oh, so I hit a brick wall, a conceptual brick wall I can't get past, so I have to go back and do a bunch of math study, but oh well.
Interesting problem, or?
So there's this technology called NeurFields, or neural fields, and they're used to reconstruct three-dimensional objects from images. And in order to use the algorithm, you have to do a particular linear transformation of a perspective matrix that I have always struggled with I've been computer graphics since I was like a kid, and I've never been able to intuitively do this stuff. And this particular transformation is literally beyond me. So I have to go back and all the way back to linear algebra and all that stuff. And I'm just trying to build up the necessary skills so I can actually understand what I'm trying to do. I don't know if you hit those walls very often, but I do. I have lots of blind spots in my knowledge. So.
Yeah, but I usually try and cheat and find my way around it.
Yeah, the Google kind of went, because the stuff is so new, and so. Oh dear. Have you encountered Bergson's paradox before?
Not directly.
Okay.
I was thinking about it though, and I think it may be very similar to a type of estimation model I have seen.
Okay.
Called a Talbot.
Look that up. TOBIT.
Correct. In particular, like if you look at the wiki,
Wikipedia, let me understand now.
It's a form of selection bias.
Yes. So it could be very similar. I mean, it's certainly in the same semantic space. So let's have a quick read.
So I think the one that might be relevant, I think is called a type 3 Talbot.
Type 3, okay. So, sorry, one second. Sorry, it's always fine. Type 3, so introduces a second observed dependent variable.
It's a type 2, where you have a latent variable. So if that latent variable is above some threshold,
right,
then the observations appear. If it's below some threshold, they don't appear.
Okay. So we have some, sorry, I'm just trying to work through this. So we have some data generation process here, right? Some DGP here, right? And it is generating a uniform field of data, right? So it's generating all the data that we care about, right? And then that's going through a selection bias system of some kind. So we have some sort of selection bias that is suppressing some part of the data field, right? So it's essentially knocking out, say, this, typically it's this area here.
Okay.
Right. So this filter here knocks out this, and so we only see data from these components.
Yeah, basically.
Okay. So it has nothing to do with the data generation process and everything to do with the observer. Is that right?
Yeah.
Okay.
So at any rate, from the econometrician's perspective, if what you want to do is make an inference about the relation between, say, your X and Y, given your data generating process data, so the first scatter plot there, you can kind of cleverly do it with the second data generating or with your selection bias data if you know enough about
Hi, Rose.
ooh, that's ugly.
What's that?
The audio. Oh, I'm getting it back.
Hi, good morning. Sorry I'm late.
Yeah, you're having some internet issues again today, Rose, sadly. You might want to kill your video.
Is it bad?
Yeah, pretty much.
No.
That's better. You're better now. However you did that.
Any better?
That's very good.
Okay, good.
Yeah, yeah. Sorry, we kind of get rolling. How are you?
Okay. Good. Yeah, good. How's everybody?
Good, good, good. Okay, so we kind of jumped in. Very interesting, by the way. Very interested in the whole Bergson's paradox concept. Rob and I were just talking about it. Rob brought up this concept called the Talbot Model.
Yeah, so are you familiar with that, Rose?
No, I'm not.
I'll type in the link in the chat.
I'm not sure whether it really matches up or not with this Berkman's or whatever his paradox, but it seems kind of close.
So just to explain, sorry, there's a bit of feedback, Rose. You might want to mute when you're not talking. Your audio is somewhat problematic. Sorry, yeah, I'll just walk you through. So we have some data generation process here. It's generating some pseudo uniform data distribution.
Do you want to describe it to me?
So the data generation process. I'm still getting it when she's muted.
Yeah, I might try again.
Odd. Is it me that's getting the feedback? Sorry, I'm just trying to work out where the feedback's coming from. It's not you, Rose. It's from somewhere else.
I was hearing delayed responses to my audio.
Oh, okay. I think it's your audio loop because your sound cancellation can't deal with latency. Perhaps you should switch to headphones. Maybe that'll help. I don't know if you have them. If you don't, that's fine. Anyway, sorry. Okay, so we have some data generation process rows here, and it's just some data generation process. And we're saying the I'm just trying to describe Bergson's paradox in my understanding so that we can clarify my understanding because I don't have a good understanding. So the idea is that this generates a field of data points. And then those data points are then essentially subject to a selection bias where we essentially suppress part of the information, and it's also apparently more like this. The suppression field tends to be more like this, and then this introduces this correlation, this negative correlation along this axis that doesn't exist in the original data generating process. Is that a reasonable summary?
I think I guess it depends what you define as the data generating process.
Okay.
Because what we're really thinking about as data, the selection bias happens before you even get to data.
Okay,
you know what
so
I mean?
the selection bias is actually internal to this.
it's coming before
Well,
the data generating process. If we're saying that the generating process is generating an EHR, a set of EHR data, right? The selection bias is happening because we're only seeing sick people.
right, yes.
But so in theory, there is a broad data generating process. And what we're doing is we're selecting that based on the patients that are in the hospital.
Yes, exactly.
Okay,
And I think that's the thing that we often talk about the data generating process, assuming that our data is a complete reflection of the data generating process, but it's not. There's a set of selection happening even before that.
Yeah, but I think David's diagram would still work there.
Okay.
Yeah, so there is some underlying non-human data generating system that's spewing out, you know, sick people and you know, well people and healthy people. And then there's a selection bias, which is I don't go to the hospital when I feel well.
Right.
Right. But if you consider the data generation process as the person sitting at the hospital typing information about patients into the system, then you are correct. At that point, the selection bias is already occurring. So I'm just trying to clarify.
And this is the problem with observational or retrospective studies compared to, I mean, even a randomized control trial, right? It's already sick people that are in there. And we claim it's random, but it's not really, like, we can't ethically do randomized studies for the most part.
So this is a profound and deadly problem. Are we dead in the water?
No.
Okay.
I don't think. I may be missing something here. Let me just find this here.
Okay, so I'll make a weak case for the deadly problem, which is we have no way of sampling the unselected samples, and so we have no idea how big the filtering is. Like if I have a hospital and I live in a community of incredibly healthy people, and I have very, very few people who show up at the hospital at all, I have no idea how big the population is. So you kind of have to, how do you fill in the missing piece?
Yeah. It's a really hard problem.
Yeah, okay. So I think there are kind of econometric approaches to it. They don't necessarily solve it. I mean, they kind of solve it by making more assumptions.
Okay.
So let me, can I
Sure,
keep the screen?
Yeah, I'll stop. Yeah, go ahead. Sorry. I'm just trying to frame the problem. That's all.
Yeah, no, understood. Okay, so this is the, you see the Talbot model? Okay, so it's just a wiki page on this. So actually, I misspoke earlier. I think this is more like a probably a type 2 Talbot model. Okay, so what's going on here is essentially we observe data if some latent threshold is above a value.
Right.
If that threshold is below the value, we don't observe it, or we may just say that it's got the value 0.
Sure.
Okay.
I mean, does this sound like, I mean, this is...
I know, but we have no idea what the threshold of
Yes.
Y1 is.
Yep, that's part of the problem here. Yep.
And we also don't know what proportion of the population falls within that lower bound.
Right. So just talking about a very practical example that I think everybody can understand. When we look at the COVID vaccination studies, so like in many ways, this is as good as it gets with a randomized trial, right? Because we have very, very large numbers and it was done on a global scale.
Right.
But then we start to see these studies come out. I know that Kaiser did one, I don't know, maybe 6 months ago now. And that the purpose of the study was to show safety of the vaccine, right? But what the study showed was that vaccinated people had lower death rates across the board. Not death rates from COVID, but from everything, right? And this is sort of put out as like, oh, this is great, great news. And I look at something like that and I'm like, that's not great news. Like, what's that telling us is that there's something else going on with the people who are vaccinated or not vaccinated that has nothing to do with the causal chain for COVID. There's something else happening there.
Right.
And this is why it's these are
Yeah.
problems to solve, right? Rob, you look like you're
Yeah, no, I got
You're
two screens
certain.
going. Let me move this over so I'm looking closer to the camera now.
I wasn't trying to shut you down on the Talbot stuff, by the way, at all.
No.
Yeah.
So I don't know. My view is that all these estimation problems are fundamentally solvable, but you have to think about them intelligently. You can't just, like your COVID testing one is a good one. So I don't know. How would you approach that? Well, one thing we could do is to say, okay, let's look at a sample of people who have chosen not to become vaccinated, and let's look at them on a bunch of dimensions, and let's do the same thing for the vaccinated guys.
Mhm.
And my hunch is you probably start to see differences. I mean, you've already told us that there is a difference.
I guess the piece of it that drives me crazy is that that's not what the conversation ends up being, right?
Oh, correct,
Like
yes.
it ends up like, oh, this is great news. And it's just like, hang on a second, this can't be great news. Like this is showing us that there's something here that we just don't understand. Like, but yeah, I agree with you. Like if we take all of those things and move forward and try and untangle that, like what is it? What's the real cause here?
Okay, so sort of, I mean, I'm making this up as I go, but what I'm trying to, I guess, describe is how I might approach the problem. I don't know, suppose I was able to get actuarial data on people who look like the non-vaccine takers, and look at their historical death rates.
Mm-hmm.
And then do the same thing for the vaccinated type. There are going to be a whole bunch of other stuff that's probably going to be related to that. But suppose if you had that, then essentially what you could do potentially is to look at the likelihood. You could kind of separate it into two groups and do an analysis on the likely vaccine takers. And then if you had enough data, you could separate those out. between those who did and those who didn't, and get sort of a more of a better control group. I think this is what the Heckman selection bias stuff is trying to do.
So if I'm understanding you correctly, what you're trying to do then is basically go find latent variables. You're trying to bring more data sets in so that you can understand
Yeah.
what are the latent variables.
I'm trying to, I guess I'd be trying to do something that would allow me a better control group. So in the latent variable problem,
Sorry, can
Oh,
you
yeah.
carry on? I'm trying to draw what you're saying. Sorry. And if
Yeah,
I'm
no,
not doing
so
that-
I'll have to get, like, it's been decades since I've looked at Talbot models.
That's fine.
But my recollection is, if I'm thinking about it, it's a little different. So it's not like we don't have data on the people who were filtered out, but it's more like we've got, we realize we don't have any observations for them, but they are there. So this actually matters in the likelihood function for the estimation.
Mhm.
Because now you're essentially saying there are two portions. The portion for which you have the data conditional upon the latent variables being above some value, and the portion that you don't have data on conditional on the latent variable being below a threshold. Okay, but that's different. That's different from saying you don't know anything, because you kind of know the fractions.
I see. So you're suggesting, if I understand you, that there's this line here, and I'll delete this one, sorry. There's this line here, and we know that that line exists. Right, there's some separation criteria that our selection bias is applying, which is hiding information that would otherwise be available in the data set that we have access to.
Yeah, I guess so.
How do you know, tell me again how you know the fraction, Rob? Have you gone out and done another random sample across the entire? Is that what you're saying?
Um,
How do you quantify how much of the overall population you're seeing?
okay, so usually that comes from other information. Let me see if I can remember this. This came up in educational studies where they're trying to look at the impact of college on earnings.
Mm-hmm.
Okay, so there is obviously a group of people who didn't go to college, and maybe your sample is only college graduates. So you could potentially go back and look at, take San Francisco or something. You could, if you went back in time, you could say, okay, X many people graduated from high school. Some fraction of this went on to college. So you would kind of know what that split is.
Mm-hmm.
Right. Yeah, so to say that in this, say exactly the same idea in a slightly different way, we have a data generation process. It is outputting data. We sample that using our selection bias because we're now recording data at hospitals, but we could also take a different path and try and represent the complete data set in some control. We could then extrapolate what, based on the proportions that we see in the data generation process, we could essentially fill in the missing piece, the suppressed piece here, and then feed that in to try and renormalize or
Repopulate.
Fill in the missing pieces of essentially to overcome the selection bias. So my
Yeah, I would
point
think
is,
so. Okay, I mean, okay, all this is going to be sloppy, right?
yes.
Okay.
I think that's that Birnbaum paper of like where he takes different data sources and then tries to build a DAG so that at any point in time, you're trying to falsify the DAG as you know it and identify different latent variables that you might need to know about. Do you remember the paper I'm talking about?
Yeah, I
Yes.
kind of remember the videos. But does that still have the selection bias data problem?
Yeah. Well, so I mean, he's trying to come up with ways to get around that. And right now the implementation is pretty simplistic, or it was the last time I looked at it, in terms of it will tell you, oh, there's a selection bias here and you can't do what you're trying to do, right? Based on the data that you have, you can't make the assumptions that you're making.
So
I
he's
mean,
essentially challenging us to disregard the data as being meaningful.
yeah, like I think it's like in this situation, the piece of this data set that you're using, what you're trying to do is okay. Whereas, if you're trying to do something else, there's a selection bias there, and you can't really generate a reliable estimation using the data set that you have. And I mean, I think over time, right, you can refine that more and more, understanding how to, I think kind of what you're talking about doing, Rob, like is looking outside the other data set or the data set you're working with, and trying to find other ways that you do kind of crude estimations of, let's say 25% of the population, we believe 25% of the population. Now does my DAG align given that?
Right.
Like, have I identified that I think it's whatever, poverty or...
Yeah, so I mean, so this is a standard econometric solution. I can't solve this problem. Let me start making assumptions until I can solve it.
Right.
That's, it's not a bad approach, but this is, all right. Yeah, this is one of Jim Heckman's papers. He actually won a Nobel Prize largely for this. So there's a R implementation of it.
But can we kind of try and gain a sense? So he recognizes that a selection bias is in play, and he's trying to infer information from the data that he can access, even though it's come through this selection bias, to estimate what the selection bias has suppressed. Is that?
I think that's the idea, yeah.
Okay, but we're not trying to find a separate data path. We're trying to find underlying latent factors that are present in the data that we could use to extrapolate the missing information.
Yeah, something like that. I'll have to go back and look at it.
I'm happy to look at it too. No, this is very relevant and very interesting. So basically, whenever we have a situation where we have some latent variable that remains latent until it reaches some threshold, exactly as you pointed out, then it becomes salient to us. But below that threshold, it's not salient. And we're trying to infer non-salient data from salient data. This seems very dodgy to me.
I don't know, I mean, we're doing that all the time in the real world, aren't we?
Yeah.
So dodgy or
bad
not,
decisions
I mean,
in the real world all the time. But anyway, yes.
Kind of describes my brain to some degree. Yeah, do I pay attention to this or not?
Well, I think the difference is that once we put numbers around it, there's an assumption that it's real, right? As opposed to, well, that's just your experience.
Okay. So I get it. So basically, there has been some very good work done on, I would suggest that there's two paths that we've talked about so far. One path is to augment the sample biased data with data that either suffers from different biases or doesn't suffer from any bias, and then use correlations between the information that we do have in the sample bias with the unbiased to essentially infer the missing information. And then there's a second approach where you only have the sample bias information and you essentially try and extrapolate the missing information using latent variables within the data that you have. Are they different, or am I saying the same thing in two different ways?
I think they'd be different.
Am I missing the third one, the Barenboim one, Rose?
No, I think it's captured in it. Like you're saying where you're stating the assumptions that you're making, and you say, was this randomized data set, or was this an observational data set? So I think you capture it.
Okay.
Sorry, my brain has gone back to the clustering idea that we've been talking about, and this idea of given that you're working with a particular data set and you've built a model on that, and if we can, through clustering, replicate a classification, right? But then use the clustering to identify that a drift is starting to happen. It might help us to identify where the selection bias is now impacting our model, and help us maybe even find the latent variables. Sorry, I'm saying a lot of words. I'm thinking about
it makes sense.
Yeah, that again, coming back to, can we use that idea of clusters versus classification to identify a drift happening between our explanation, which is the classification, compared to our reality, which are the clusters, or our reality within the data set. Does that make sense?
It does. It does. I just want to draw one more picture because it helps me think, and I hope that it's helpful for you. It's a different picture, so I'll actually create a new sheet if I know how to do that. Yeah, okay. So we have a time series, okay? So this is time. At this point in time, we see, we have a bunch of agents okay, so we have a bunch of, I think the arrow is wrong. So at this point in time, I'll get rid of this, sorry. At this point in time, we have a set of people, right, in here. And you're correct in saying that we have classified them. This is our classification. And then at some later point in time, we have that same group of people, and our classification would only classify this subset, and these people we would classify differently. And some action has taken place between time t1 and time t2, which has allowed these people here to take some series of actions, pass through some Markov blanket that moved them from this classification to this classification, right? Now, we can do this with standard classification mechanics and see how populations are moving from one classification to another, and we might even be able to look at the subpopulation and infer what the actual action was that allowed them to make that jump. Now we have to introduce clustering, and this is where I'm not quite understanding how we can use clustering. So we can do this kind of state change analysis over time with classification, I think.
So
Or have I
I'm going to
misrepresented?
challenge you, and I don't know if I'm right or not, but
That's fine. I don't know if I'm right, so it's all good.
So I think the problem is not that at time 2 they're moving from one classification to another, but that our model is putting them in the first classification, even though that's no longer the case for some reason.
Okay. So what?
And that if we were using clustering instead of classification, clustering would see that there's something different happening here.
Right. So we would have some, so we built our model based on the fact that we saw this cluster, but our model is not resilient to the fact that we now are seeing these clusters. And so we can speculate that our model is wrong.
Yes, yeah, and I'm going to, again, correct on one word from the way I'm thinking about this. We created our model based on these classifications, not on clusters, because we did it supervised, right?
Well, okay, so
then we aligned our...
What's the difference between a cluster and a classification here?
So classification is supervised, clustered is unsupervised. And what we're trying to do is see if we can generate clusters to match our classifications. And if at the time we create the model, we can create a cluster that matches the classification, right? And then after the fact, as our data set evolves, we start to see that there's a drift now happening in the clusters, but our classifications don't stay the same, right? Because our explanation hasn't changed. We haven't updated our explanation yet.
Right. So
yeah, I mean, that seems pretty tractable.
Yeah. So we have our model, right, which is a data generating process. And this is inductive or deductive, right? So we have an explanation here, right?
Can we remove the data generating? Because this is very confusing. Like,
okay.
When we're talking about data generating process, can we say that when we say that we're talking about the general real world activity?
I misspoke.
And making no, I know, but I think it's a really confusing thing, and we're not the only ones who do this, but we assume that our data is a complete reflection of a bigger reality world. I mean, maybe we need to say like the reality data generating process or something compared to the technical data generating process or the data set generating process.
Here we go. I'll
okay,
take
so call it an S.
I guess they use is a big world, small world. Big world. Is that's terminology that I've heard other people use?
Yeah, or you could just call it a selective data process. So it's already been filtered in some way.
An explanation-driven process. Yeah, an explanation-driven generative process, right? That would be, I have this, F equals MA, I have this model of the world that I can explain to you that would generate this data, as opposed to an observational. Well, no, both. Yeah.
So the application I'm thinking about for this, it might just help to make it a bit more real world, is that we have, like, in terms of defining a disease and a treatment, we have these ways of saying you fall in that category or you don't, right? And so in a simple binary case, we're saying you have this disease or you don't have this disease. It might be based on, for example, a single lab result combined with some symptoms or something, right? And then it puts you in either classification. Yes for the disease, no for the disease. Initially, that diagnosis was coming about for a very small number of people. But through success of the treatment, the population has been expanded. And now maybe that the original criteria for diagnosis no longer matches. Like we're not getting the results that we expect to see in the broader population.
Okay, rewind that a little bit for me. I want to make sure I understand it.
Mm-hmm. So I'm going to talk about the thyroid thing because it's the one that I know the best, and I think it's a good example of this. So at one point in time, this was a relatively unusual condition, and it was like a very, very serious condition where people were very, very sick when they had it, and bodily functions were majorly impacted. And so we have a lab result that we go test in this situation, and it's like, if it's above a certain level, then we have a serious problem here, and treatment is indicated. And because that treatment works so well for those patients, then more and more people started to want the treatment. And so as we start to do the test on a broader population, we're seeing that that threshold that we've set maybe isn't as set in stone as we thought it once was. And it's different in different populations. Right, so the classification algorithm that we're using, which worked very well at some point in time when you were talking about a very seriously ill population, when they start talking about applying that at the larger population level, meaning everyone, let's proactively go out and test everybody for this, we see very different results, right? And the same thing with the treatment that worked really, really well for the people who are very sick, when it's applied to a broader population, it doesn't have the same impact.
So in those analyses, was the criteria for the test result, was that modified or was that kept the same?
So over time, they've lowered the threshold.
Right. Okay.
Because more people were like, well, we should try and get in front of this, right?
Yeah. Oh no. Yeah, it makes a certain amount of sense. Yeah.
But then what they're finding is even when they do that, they're not getting the results that they thought they were going to get, right? Because the treatment is not working the same way for the broader population. And so there's a drift that's happened, right? The sample that this was all tested on and identified on, both with treatment and diagnosis, those same things they're not playing out the same way in the broader population.
Yeah, there are many sources of bias here that scare the heck out of me, but
yeah, it's a really hard problem, right? But it's, again, if we can try and find, so right now we have a classification algorithm that's yes, no. And if we could match that classification with a cluster, but then identify a drift that's happening in the cluster that's perhaps using an entirely different set of features.
So what if we supervise the clustering algorithm with data at time t=1? And then...
Hang on, I'm not with you yet. I need to picture it.
Oh, sorry, let me bring up the picture again. Sorry.
Yeah,
It's the same picture, sorry. So we're here, and we have a model-driven, we have a set of beliefs around what's going on, and we use that to we use that to simulate data, right? So we generate data that's a simulation of the model, and then we essentially use that model to find a cluster in the data. Okay.
The model is supervised by what?
the model is generated by my set of beliefs that there's this thing called an X and it has this logarithmic relationship with this other thing called a Y. And so I'll generate some random values of X and I'll take the logarithm and then I'll get a bunch of values of Y and I'll call that truth. Okay. And then I will generate given some data, I'll try and cluster the data so that it agrees with my beliefs.
Yes.
Okay. At time t equals 1. Okay.
Yes. Yes.
And then I take that cluster that was essentially fitted to my beliefs, and I apply that clustering mechanic at a later time, and it does not agree with my beliefs. What does that tell us?
Yes, that's what I'm trying to get at.
Okay.
But if we can, so another piece of that is that if I can find some other cluster T2, and I can explain how we got from clustering A at T2 compared to clustering B. If we can identify how the drift is happening between the clusters, then that tells us something about latent variables, I think, and tells us something we have to learn about our explanation.
Right. Our explanation is either wrong, which it could be, or is simply incomplete.
Yeah, so to make that work then, you need, or it'd probably be best to have some type of parametric clustering algorithm. In other words, you observe data, you create a model that takes those numeric scores of that data and maps it into a cluster. So, but if you have
I'm sorry, I'm lost again. Go back a second, Rob. I just want to make sure I'm tracking with you. Repeat again what you just said.
Okay, so suppose at time 1 you've got a numeric algorithm that takes the observed values and maps it into a cluster. But this is you're fitting that to the data, so this is sort of a deterministic model, if you will. Then when you look at
so hang on. So at T1, we have, let's just take the simple case of a binary classifier. So we have 2 supervised classifications that we have explanations for, and that's our algorithm. And then at the same time, we're trying to then cluster using a broader set of features, right, to match the classification. Are we in agreement to that piece or no?
Yeah, okay. So I mean, I'm trying to figure out a way of operationalize what I thought was you were getting at. So we could do it in clusters. We could also do it in with the supervised learning too. So we could take the time 1 model. We could build a supervised learning classification on it. Then we could take the data at time 2 and repeat that process, but there's a wrinkle. So at time 2, we could compare basically the success of the time 1 parameterization versus re-estimating it again at time 2.
Mm-hmm.
So we could look then at the difference between those successes as a measure of the drift.
Mm-hmm.
Is that kind of what you're trying to get at?
Yeah, something like that.
But what if the drift is real? What if the behavior, the information has been distributed in the population that has changed their behavior?
Yes, that's exactly what I'm talking about though. But recognizing.
So what's wrong with that?
There's nothing wrong with that. Like it's except that now your explanation no longer matches, right? The algorithm that you're using.
Yeah, right, your time 1 explanation doesn't work as well.
Your time 1 explanation does not only doesn't work as well, but at time 2, it's starting to fail. And by time 3, time 4, you're playing an entirely different game and you don't even realize it.
But isn't this a problem that marketers have all the time when
I show you ads of stuff you've already bought. Yes.
well, I mean, yeah, so you've got I don't know, some type of promotion to try and drive up sales. Now that influences the behavior. And then essentially don't you have to basically go back and reestimate the model then, conditional upon what the promotions that you've already given them?
So I would say the difference in medicine is that often we don't update the algorithm. And I'm not talking about a technical algorithm or a machine learning algorithm where there's a classification. It's that we've sort of said, this is how we make a diagnosis. And that stays the same, even though the population is dramatically changing, right?
That's a good way of putting it. Yeah, it's very clear. Yeah, okay. So we have a persistent belief. The problem here is a persistent belief. It's not that we're stupid or that there's something horribly wrong. It's just these things linger longer than they should.
And, well, and there's also the belief that there isn't a dynamic process going on, right? That once you've done a randomized control trial, that answer is correct, both now and at any time in the future. Even though there's there are things happening to the population that were not reflected at the moment in time you found that truth. It's not that that wasn't true. It was true for that population at that moment in time. But things have gotten more complex. And especially when you look at the polypharmacy, right? The populations are becoming far more complex.
Very interesting.
All right, well, it's taken us about an hour, but I think we've solved a major problem in medicine.
If only that was true. But do we have a way to, do we think we can maybe find a way to use the clustering to identify?
Yeah.
So I don't think we've resolved that yet. I think we've talked about supervised clustering as a mechanic to do that, which I think we should try and see if that has veracity. And I'm willing to put some effort into that. But there's still an unanswered question in my mind. And that's not that it's, it's not a problem. It's just we haven't introduced unsupervised learning into this picture, right?
I think we have, because I don't think it's it's only supervised at T1 till you get to the point of matching your cluster to your classification.
Okay.
So matching unsupervised to supervised. And then what you're doing is, by the time you're getting to T2, recognizing that no longer works. You cannot match.
Right.
So, yeah, I mean, my interpretation, this kind of gets back to what you were getting at earlier, David, when you're talking about RCTs and clustering.
Right.
So the traditional medical approach would be, okay, we got new data, now we got to do a new RCT. Okay. So we have to do that at time 1, at time 2, at time 3, and whatever. So we kind of start over. But what I was taking away from your discussion was kind of a merge between your ideas and Rose's. But if you could see, if you could, instead of doing an RCT, if you could do clustering sort of at each point in time, and maybe you do the clustering with the original data and try and match that up. And then if you have some sort of parametric version of that clustering, then you can take time 2 data, you can look at the clusters using the parameterization from time T1, and you can compare it with sort of a new parameterized version and say, okay, which one does better? So is there evidence of a drift, and can you pick it up in the cluster classifications? I think the answer to that's probably yes.
And can we build a model that anticipates the shift in the unsupervised clustering? Because that would be a super duper model if we could do that.
Well, ex post, we probably could. I mean, ex post, we can say, okay, so what we should be able to do at time t equals to 2 is look at the clusters that were generated from the t equals 1 parameterization versus those from just the t2. And we should be able to untangle why those clusters changed. I mean, in some sort of, cart type framework or something.
That's the piece of it. I think we need an explanation to be able to point to some difference there. And if we can do that, that's very powerful.
Slow down. I mean, that would be nice, but if you were merely able to say the world has changed and we don't really understand why it's changed, but it has changed, and therefore the medical decision rules you've been making, you might want to rethink those.
Yeah, that doesn't work.
No, it's better than just sort of press on regardless.
Yeah, we're coming up to time. I actually think we've covered a lot of very useful ground here. So Rob, you actually did it. You actually gave us a path by which we could use the unsupervised learning in this time series, which I think is very interesting, which is essentially don't look in the past. When clustering, don't look at historical anything and don't look at models, just cluster based on perceptions or data. And then see how those clusters evolve over time and use that as the intuition to drive your explanation. And I think that's a really interesting idea. So I don't know if that was coherent, but essentially what you're saying is that we should be doing unsupervised clustering in a cross-sectional form and in a time series form.
Sure.
Right?
Well, I'm just trying to operationalize what I thought I heard Rose talking about. That's all.
And you did a great job. So I think that kind of captures it, which is take a data set at a point in time, use unsupervised learning to cluster that data, rinse and repeat at different time intervals of time, and then look how the clusters evolve to form your intuition about what's going on. And don't generate a deductive model at the outset, and don't do supervised learning, just do unsupervised learning over a series of time steps, and then see how that unsupervised cluster changes as time changes. And that should give us some relevant insight. Maybe. Does that make sense, Rose? Sorry.
Mm-hmm. Yeah. Yeah, that's exactly it. Yeah.
Why can't we do that? I mean, can't we just do that? It's just a question of collecting some data and throwing it into the unsupervised learning algorithm, which I already have working, and see what emerges. No?
How hard could it be?
Very hard indeed. I'll be the first to admit. But
I mean, I think the data set is the hardest piece. I mean, that's been my experience with everything in medical, anything. Like,
if you're tracking the same population, that is invariant across samples, no?
I mean, I'm talking really practically, like getting your hands on a medical data set where you could do this.
Okay.
Right? And then doing the work to get that to a point where it's a clean enough data set that you could start to run some of this stuff. Like, I guess I feel like a medical data set is not the right place to start, but if we could do those ideas with some other data set that's available.
Or synthetic.
And,
yeah, I've got a possible example, real data.
Okay. I think if we could build it with the real data in some other thing, then we could make the argument to get the medical data to do it. But trying to start with medical data, it's going to be tough.
We're at time, Rose, and I know you're very time sensitive, but great discussion. I think this is worthy of a write-up, so I might actually try and write this up and put it in as a comment, just to see if I've captured the critical ideas here. But I think that this has been a very useful discussion. So.
Yeah, so the example I was thinking of is bond ratings. So when you look at bonds, universal bonds, they are rated like, you know, really low default risk, medium, high default risk. So technically there's going to be like a AAA and then a AA and a single A and stuff.
Mhm.
But what really determines whether it's a AAA or AA is kind of unspecified, and I think that tends to vary over time.
Right. The explanations change.
Well, the criteria that, I mean, there are professional groups who go out and do this, but their criteria, I think, changes. So in that sense, there's a drift in the underlying data or the models being applied to that.
I think that sounds like a good example, and it's complex enough that it's, you know, sort of.
But yeah, but we could presumably get data on the ratings, and you could track it over time, and you could relate that to, you know, the fundamental characteristics of the companies and stuff. So this is why I like finance. It's medicine made simple.
Okay, let's definitely take a crack at that, Rob. If you could collect some data, I'm very willing to throw that into the pot and see what comes out.
I'll investigate and see what I can dig up.
Okay, Rose, as I say, I know you're sensitive on time and we're over time now. So shall we call it there?
Sounds great. We'll talk next week.
Okay.
All right. Thanks, everybody.
Thanks, and I will do a write-up. Thank you. Okay.
Thanks. Bye.